And action.
Thank you. All right, today we're talking about gas stoichiometry, density, and Dalton's law of partial pressure. When we're using stoichiometry in gases, we have to make sure that we are at standard temperature and pressure. Standard temperature and pressure are defined as 273 K, which is the same as what in Celsius?
0.
And the pressure is 1 atm. And under these conditions, 1 mole of any gas, by virtue of the fact of Pervner, where P and T are the same, R is the gas law constant, so that means 1 mole of any gas always has the same volume, which is 22.4 liters. That's called Avogadro's law, and it's very helpful. Gas stoichiometry is a combo of a stoichiometry problem that solves for the number of moles or the volume of a gas, and then you put it into a gas law formula or vice versa. So here comes our first one. Remember, you can tell a lot from STP. It's a lot of variables. A sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles are present? What formula should we use? Pervner, where the pressure is 1.0 atm. The volume is given at 1.75 liters. N is what we're solving for. R is a gas law constant, 0.0821 latma molka. Latma molka. I go to Starbucks and I order a venti latma molka. You say. Latma molka. Say it again.
Latma molka.
Why am I bugging you?
Do you remember?
Because I want you to recall the units that are acceptable in the ideal gas law. Must be in liters, must be in atm, mole is the only way I know how to express that, and it must be in Kelvin. So don't mess up. Latma molka. There you go. Substituting into the equation, the number of moles is equal to this number right there. Well, that wasn't bad. As long as we stay at STP, everything's fabulous. All right, exercise number 12, gas stoichiometry 2. Quicklime, calcium oxide, is produced by the thermal decomposition of calcium carbonate, CaCO3. Calculate the volume of CO2 at STP produced from the decomposition of 152 grams of calcium carbonate by the reaction. Calcium carbonate decomposes into calcium oxide plus CO2. Did you know that any metal carbonate decomposes into the metal oxide in CO2? Don't you wish you had known that on Tuesday?
Sure.
Yeah, but no. Okay, but now you do. All right, let's plan how we're going to do this. First of all, what do they want to know?
The volume.
So we want to know how many liters of CO2 are produced by 152 grams. And we're at STP. All right, there's a number of ways to do this. Let's do one of them. Well, I think I could figure out the number of this, and then using stoichiometry figure out
The number of grams or moles of CO2 and then go to liters.
Let's do that then. So I would like to know the number of liters of CO2 equal to 152 grams of calcium carbonate. 1 mole of calcium carbonate is how many grams?
3 plus 12 plus 48 is 100.
100.
Okay.
Now, you know what? Good for you, because a lot of people are just writing down what I'm doing. You need to do these problems with me, or independently, you're not going to be able to do them. All right, my next step should be what? Moles to moles. 1 mole of calcium carbonate, 1 mole of CO2. Now what? 1 mole of CO2 is 22.4 liters. Check the math. Okay, that worked out for us. If this had not been at STP, this would not have worked. You would have had to change this into moles and then put it into Perkner.
Could we have done dimensional analysis on exercise 11 as well? What did you?
Probably. Yep. A sample of methane gas having a volume of 2.8 liters at 25 degrees C and 1.65 ATM was mixed with a sample of oxygen gas having a volume of 35.0 liters at 31 degrees C and 1.25 ATM. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of CO2 formed at a pressure of 2.50 ATM and a temperature of 125 degrees. Huh. What should we do first? Do what?
Right out of the equation.
Balanced equation. I'll spot you the methane is CH4. Now what?
O2
plus
O2 always yields
CO2
and water. And a little balancing is in order. So what would we like to know? So once again, we're looking for the volume of CO2. Are we at STP?
No.
Oh, that ain't gonna work then. So what should we do?
plug in stuff for easy.
What stuff?
The reactants.
You have 2 reactants,
Okay.
and you want to know how much product is formed.
Oh, for the limiting reaction.
There's going to be a limiting reactant involved somewhere. Okay. A limiting reactant using volume?
No, you just calculate it.
Yeah, you just calculate the number of moles and
Oh,
then,
yeah.
okay,
Yeah.
I see what we can do. So, let's see here, up here, I'll use this part. I'd like to know the number of moles of CH4, and I'm going to have to use Perkner, correct? It is not,
Can you just do 35 divided by 22?
nope,
Yeah.
why can't I?
It's not
Oh,
STP.
because
It's not at STP.
Got it, okay.
Okay. 1.65 ATM, 2.80 liters. N is what I'm looking for. R is 0.0821 lat/momolka.
398.
And my temperature is
398. Not that.
290. Okay, and then N, forgot to do the math part. N is equal to N is equal to
.1.
0.189 moles of CH4. So 0.189 moles. All right, now I need to know the moles of O2. And I think I'm going to use perv-nert again. P is going to be equal to 1.25. V is equal to 35. N is my unknown. R is 0.0821 lat-momolka. And T is 398, huh? So that's 1.25 times 35. It's 125 and 273. What is that? 398.
Oh, I'm sorry. Wait, isn't it 31?
Oh, it is. It's 31. Sorry. Yeah, we got carried away. 31. That's for the next part. 304. All right. The number of moles is 1.75 moles of O2. So now let's find the limiting reactant, starting with the CH4. If I use up 0.189 moles of my CH4, how much CO2 will that make? When I use my mole facts, 1, 2, 1, 2. 1 mole of CH4 over 1 mole of CO2, and that means I can make 0.189 mole of CO2 if I use up all the CH4. For my oxygen, I have 1.75 moles of oxygen will make how many moles of CO2 over its mole facts? 0.875 moles of CO2. So 0.189 is smaller than 0.785, so the CH4 is limiting, and it's making this many moles of CO2. Are we there yet?
No.
No.
Oh.
We need to find the volume. Ugh. How do we do that?
Put it back into perv-nert.
Back into perv-nert. This is like a perv-nert circle here, where the pressure is 2.50 atm. The volume is what we're looking for finally. We know the number of moles. R is 0.0821 lat-momolka. Now we got that temperature of 398. So 2.50 times X is equal to 0.189 times 0.0821 times 398 is that. Ooh, that's a lot of work. Been a lot easier to just write 2.47 into the blank. Okay. Moving on. All right, ladies and gentlemen, there are 3 things a chemistry student of mine will know for the rest of their lives. Number 1 is cations are positive. Number 2, the ideal gas law is perv-nert. And here comes number 3. Are you ready for it? It's one of my favorites. there's a cat reference to follow. The molar mass of a gas, the molar mass of a gas is related to cat. How many people have a cat? No one in this class has a cat?
Behind you.
Goodness. Jeez, that has been a bad reference otherwise. All right, for those of you who have a cat, I'm certain you probably won't admit to it out loud and proud, but you've watched your cat in the litter box.
Goes outside.
And you know that meow meow throws dirt over his pee. Meow meow throws dirt over his pee. It is true. So here we go. Number 3 in the chemistry hit parade, 2 of which happen to have cats involved. Molar mass equals dirt over pee. So this is not given on any of the green sheets. So this is one you need to memorize. The thing you have to be careful with is because we're using R and the units of R are latmomolka, the density must be reported in grams per liter. You are very accustomed to grams per milliliter. Can't use it here, got to be grams per liter. Alrighty then. The density of a gas was measured at 1.50 atm and 27 degrees C and was found to be 1.95 grams per liter. Calculate the molar mass of the gas. Remember, this only works for gases. Molar mass is dirt over P. We know that density is 1.95 grams per liter. R is the gas law constant. T is temperature, and that is 300 K. And P is equal to 150 atm. Substituting into the Wonder equation, we have, and actually this isn't the Wonder equation, there's a Wonder equation that comes at the end of the year. It really is wonderful.
How many gas you can solve all of the chemistry problems?
No, but it's this really nasty thing to solve, and somebody way smarter than me simplified it to like 2 or 3 keystrokes on your calculator. Okay, 32 grams per mole. If you had to guess what the gas was, what would you guess? Oxygen, good. There you go. All right, now, Dalton's law of partial pressure. For a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. What are they talking about? Okay, wake up. I have a virtual balloon in my real hand. What color is the virtual balloon?
Red. Oh.
Clear.
I was just asking you to tell me your favorite color. Okay, so I'm going to give the virtual balloon to 4 real students, and I'm going to ask them to put some of their air into the balloon. Here, don't let any out. Once you let any in, go ahead.
Okay, I got it.
I do not. Okay, now can you tell the volume's increased? Yes, and the volume's increased because now in the balloon, I forgot to give it to you, we have John gas, Stephen gas, Arabella gas, and who was the other gas? Carol gas. Okay, the total pressure in this balloon is equal to the pressure of Stephen gas, John gas, Carol gas, and Arabella gas.
So it's just average?
No, it just adds up. Okay, now I'm going to let the balloon go, and you make the balloon letting go noise. Ready, set. Take it. Okay.
This will be interesting. This will
my YouTube friend a bit. I really, really like you. All right, now, this takes way more paper than I've allotted, sorry. So, that's the basic premise. You just add up the partial pressures of each gas to get the total. So this is partial pressures of each gas. All right. Mixtures of helium and oxygen are used in scuba diving tanks to help prevent the bends. The bends are caused by dissolved oxygen gas in the bloodstream. And as it comes out of, as you rise up, as you come out of the deep pressure, it comes out of solution, the solution being your blood.
So it creates bubbles.
It creates bubbles, and as those bubbles are trying to escape the bloodstream, it hurts like fire. People say it burns really badly. You know, those capillaries are really tiny. So they do mix helium and oxygen together. And another interesting fact a kid told me last period, and I do know this is true, that you are not advised to fly and dive on the same day.
Yeah.
Because you're going from where there's very little pressure on an airplane to very much pressure under the water. So I'm not going to be doing that.
Such for like James Bond or something.
Yes, or you could just go into one of those hyperbaric chambers, which I don't have one, but they have those hyperbaric chamber things. Okay, a mixture of helium and oxygen gas are used in a scuba diving tent for this dive. They put 46 liters of helium at 298 K, 1 ATM, and then in the one tank, that's what it had, and then in the oxygen tank, that was 12 liters, was also at 298 K, and also at 1 ATM. So these are the two tanks they started with, and then they're going to combine them into another tank that is 5 liters big. They want to know the partial pressure of each gas and the total pressure in the tank. What can I do with what I know now to get to pressure? I have volume, I have temperature, I have pressure, I suppose I still remember R, which should lead us to, I should probably solve for, okay, same here?
Yeah.
Moles, yeah.
All right, so here's that R again. So substituting into perv-nerd, I have 46 times 1 is equal to x times 0.0821 times 298. X is equal to, somebody do that math for me? 1.88 moles. And then for my oxygen, X is equal to 0.490 moles. Okay, so they said they put this into a tank that has a volume that's equal to 5 liters. The temperature of the tank is 298 K. I know the number of moles in the tank, and that would be equal to 1.8 plus 0.49, which is, what is it? 2.29 moles. Still no R. Thank you. So So I think I can figure this out. PV, oops, do I know the pressure? Is that what I'm looking for? Yeah, that's what I'm looking for. PV equal nRT, where this is what we don't know. The total pressure is equal to what'd you get?
Forty, 11.
Yeah, I got 42.
11.2.
Ms. Adams, you added the moles.
Is this wrong?
Is that a .49?
Yes.
That would be 2.97.
Okay. Good audience participation. 2.37. Now this should be 11.7. Is it?
11.6.
11.6, 11.7, I'm going. I get it. Actually, I think I got 11.6. The book got 11.7. All right, that's a total pressure. All the pressure from the helium and the oxygen in this tank is 11.7. And now they want to know what is the pressure of each gas in the tank. How are we going to do that? That won't help. Plug into the equation again?
No, not
We
that.
can do ratio.
Why can't you do this? So let's find the helium gas. Okay, the pressure of the helium gas is X. The volume of the helium gas, the helium itself will fill the whole container, won't it? Yes, because each gas will fill its container. How many moles of helium do we have?
1.2.
We know the gas law, and we know the temperature. So we can find the pressure of helium is equal to 9.2 atm. Doing the same thing for the oxygen, we're looking for the pressure, the volume. The oxygen will fill the entire tank too. 0.490. X is equal to 2.4 atm. Well, that was a lot of work. And look at the space I gave for you.
Yeah.
Yeah, sorry.
The partial math to get-
You just subtract.
Oh, yes, you could. Okay, once I got helium, could I just subtract to find oxygen? Yep, it's always a good idea to calculate this to make sure this is correct, though.
Can't you use the ratio?
You probably, yeah, you could. All right, excuse me, do you remember the definition of fraction?
Like a
fraction.
Uh-huh.
Less like
Part of a whole, part of a whole. So when I describe mole fraction,
Part of a mole.
I think that's
Part of a mole.
hilarious.
That's almost
It's
as
the
funny
part,
as-
it's the mole part of a whole.
That's almost as funny as the thing you wrote yesterday. Be good or beware.
Yes, that's my favorite to say to a kid when I'm going to be gone. Okay, back to this. Mole fraction and partial pressure. Mole fraction is a ratio of the number of moles of a given component in a mixture to the total moles in the mixture. What? Here, look, here's a very nice explanation that'll get you what you need. If I wanted to know the mole fraction of carbon, the part of the whole, so the number of moles in CO2 that just belong to carbon, I would do this. I would find the molar mass of carbon. First of all, I'd count. There's 1 carbon, 2 oxygens times its mass, and I would come up with 44 grams. I would like to know the number of moles in 12 grams of carbon. That's 1. The number of moles in 2 times 6, 32 grams of oxygen. That's 2. Another way I could have done this is just look at the formula and said, oh, there's 1 mole of carbon and 2 moles of oxygen. The mole fraction, which has the abbreviation chi, this is a chi sign, the mole fraction of carbon is equal to the moles of carbon over the total number of moles. The total number of moles are the moles of carbon plus oxygen. So the mole fraction of carbon is 1 mole over 3 moles, which is 0.333. This is a unitless number. It's the one time you can have a naked number in this classroom.
Is that a ratio?
It is a ratio. It's like kind of like a percentage too. All right, the mole fraction of oxygen would be the moles of oxygen over the total. That would be 0.667 because it would be 2 over 3. You need to make yourself a little note right now. Everybody, right this moment. Mole fraction, the total mole fractions must add up to 1. Oh, scared myself there.